Yes, you're welcome again. And now we are going to be looking at the Born-Haber cycles given the thermochemical data. One can use the previous examples, but using Born-Haber cycles, you'll find yourself getting the same answers. But since we have a variety of questions and the past paper questions are too many each year, if you check paper 2 for those ones who do you name, if you check paper 2, question papers are all having a question on Born-Haber cycle energy level diagram, like a thermochemistry question cannot miss. So here is a different question. We are having enthalpy change of atomization of aluminium to give us, all these ones are in kilojoules per mole. So we are given enthalpy of atomization. We are given first electron affinity of aluminium, second, third. Then we are given atomization energy of oxygen. We are given first electron affinity of oxygen. We are given second electron affinity of oxygen. They want us to draw the Born-Haber cycle, BH, Born-Haber cycle for the energy changes, and we used to capture the enthalpy of formation of aluminium oxide. Also, they want us to comment on the stability of aluminium oxide. Now, for Lash, to draw the Born-Haber cycle, any order you follow, whether you want to write from up going down, whether you want to write from down going up, it is up to you. So here, I'm going to, let me write from down going up. If I have aluminium oxide, if I have aluminium, I shall have aluminium plus 3 out of 2 oxygen. You can balance after writing the equation. This is a gas. We shall be forming aluminium oxide. So balancing the equation, you can first write aluminium atom plus oxygen, O2, to give us aluminium oxide. Then you put a 2 on aluminium. For it to balance oxygen, you have to put 3 out of 2 because we need a 3. So, and yeah, we need a 2. And therefore, this one has to cancel so that you have 3 oxygens, 3 oxygens. Now, this energy change that is going to take place here is what they want, enthalpy of formation, because we've defined enthalpy of formation as that energy given out or absorbed when 1 mole of a substance or of a compound is formed from its constituent elements in their normal state. So we are going to have an enthalpy of formation for aluminium oxide. You're forming aluminium oxide, right? Now, this one, the aluminium atom is going to undergo, they gave us atomization. So it is going to be forming aluminium gaseous atom. But remember, these are 2 atoms and they gave us for 1. So we shall have twice, and form twice of them. We shall have 2 times for 1 atom, 330 kilojoules per mole. Then after this, we are going to have the first electron affinity where we form a unipositively charged gaseous atom. And since we are forming 2 moles, we shall have 2 times the positive 578. Then we are going to form a dipositively charged gaseous atom. So we shall have aluminium 2 plus and 2 moles. So here we shall make sure that these are 2 into positive 1820. Then also here we are going to form the third. So we form a tripositively gaseous atom, and then this will be still twice positive, the third one 2750. So after this, for aluminium, we are done with what we want. So plus, now we have to come to oxygen because it has combined with oxygen to form aluminium oxide. So here we shall have enthalpy of atomization. They give us atomization energy of oxygen. So we're going to form 3 atoms of oxygen because this will cancel. So we shall have 3 atoms of oxygen, meaning it will be 3 times the atomization energy, which is positive 249. Yeah. Then here we have the first electron affinity, where 1 mole of oxygen is converted to a uninegatively charged gaseous ion. So we shall form O minus, and this will be 3 here. So since we are forming 3 moles, so we shall have 3 times for 1 mole, which is negative 142. Then after forming the uninegatively, we are going to move to the dipositively, where we shall have O2 minus, but 3 of them. So this will come this side, and we shall be having gas still here. So it will be 3. We say that the second electron affinity of oxygen is positive, that is plus 798. And then these gaseous ions, they can combine to form a crystal lattice. And this is, it was given enthalpy. What are we given? What are we given? Lattice energy is supposed to be given. Lattice energy was supposed to be given. I think I forgot it, but we can still fix it. Lattice energy of aluminum oxide. Lattice energy of aluminum oxide was supposed to be given, and it was supposed to be given as negative 15346.5. So we have it as negative 15346.5 kilojoules per mole. So looking at this, we can easily get our enthalpy of formation. So enthalpy of formation, we get it by Hess's law, and that is where we sum up everything. We shall get twice enthalpy of atomization, yeah, which will be twice positive 330 plus twice positive 578 plus twice positive 1820 plus twice 2750 plus 3 times positive 249 plus 3 times negative 142 plus 3 times positive 798. So you sum up everything together with the lattice energy, negative 15346, 15346.5. So by summing up all those, you get your enthalpy of formation, and it will be negative 1675, negative 1675.5 kilojoules per mole. Like as simple as that. So when you're told to comment on the stability, we shall say that aluminum oxide is stable. Aluminum oxide is stable since its enthalpy of formation is exothermic. When enthalpy of formation is exothermic, then the compound being formed is said to be stable. That is question 1. Question 2, I'm going to summarize it also so that it does not take us much time. So question 2, we have been given the thermochemical data, and the first one is enthalpy of sublimation of sodium, and it was given as positive 109 kilojoules per mole. Another one was bond dissociation energy of chlorine, and it was given as positive 242. Then another one, first ionization energy of sodium, and it was given as positive 494 kilojoules per mole. Then we have lattice energy of sodium chloride. And was given as negative 771 kilojoules per mole. Then we have enthalpy of formation of sodium chloride. And this was given as negative 411 kilojoules per mole. So these are thermochemical data. And basically, they want us to calculate electron affinity of chlorine. They want us to calculate electron affinity, calculate electron affinity of chlorine, but using Haber cycle. They want us to do a Haber cycle. Then they gave hydration enthalpies of sodium. Part 2, they gave us hydration enthalpies of sodium ion and chloride ion, and they were given as 406 kilojoule per mole and 363 kilojoules per mole respectively. So they want us to calculate enthalpy of solution of sodium chloride. Then they want us to comment on our answer on this part of enthalpy of formation, and we give a reason. So this is very easy because at least we are going to see what happens. One, we have sodium. We shall have sodium solid plus chlorine gas to form sodium chloride. And here we shall put a half so that we get one chloride also. So they give us atomization, rather sublimation, the same is. So we shall be forming sodium gaseous atom. And the enthalpy was given as positive 109 kilojoules per mole. Then we shall form the ion positively charged gaseous ion. And the enthalpy was given as, for the first electron affinity, ionization energy, sorry, positive 494. Then now after this, we also dissociate the chlorine. Chlorine, we have been given bond dissociation energy, but remember bond dissociation energy is for 1 mole of chlorine, and yet here we are having a half mole. So we shall be dividing the dissociation energy given by 2 because we have a half moles to form 1 chlorine atom. So we shall have positive 242. We divide by 2 kilojoules per mole. Then here, to form a negatively charged ion that will react with sodium ion, so we need a negatively charged gaseous ion, so we shall have electron affinity, and that is what they want. So when you sum up these gaseous ions, they form a crystal lattice of sodium chloride whose enthalpy of formation was given. So they gave us enthalpy of formation of sodium chloride, and it was given as negative 411 kilojoules per mole. So this is very okay. Now by Hess's law, we can calculate the electron affinity. So we shall say that enthalpy of formation by Hess's law, the theta has to be here. Enthalpy of formation is going to be equal to the summation. We shall add enthalpy of sublimation here of sodium chloride, then plus the first electron affinity then plus a half of the bond dissociation energy, a half of bond dissociation energy, then plus electron affinity, then plus lattice energy. Lattice energy was given here also as negative 771. So plus lattice energy. So when you sum up everything, here we are going to substitute negative 411 formation. This will be positive 109 plus electron affinity positive 494 plus a half of bond dissociation energy, that is 242 over 2, then plus electron affinity, which we don't know, then plus this lattice energy negative 771. So when you bring everything this side, you're going to get your electron affinity as negative 364 kilojoules per mole. So if they want you to calculate the enthalpy of solution, remember, as I told you in part B, we're in part B now, enthalpy of solution of sodium chloride, we say that it is the lattice energy plus enthalpy of hydration, yeah? But regardless, even though the lattice energy is negative, we consider it positive, so we shall have positive 771, then plus hydration energy. We sum up the hydration energy of these ions. They have been given as positive, but they must be used as negative because hydration of these ions is exothermic. So we shall have negative 406 for the sodium plus negative 363 for the chloride. When you work on this, you get positive 2 kilojoules per mole. Yeah, as simple as this. So if they want you to comment, yeah, the comment is that the enthalpy of solution of sodium chloride is endothermic, since the magnitude of lattice energy is higher than the magnitude of its hydration energy. Yeah, the enthalpy of solution is endothermic. And why? It's because the magnitude of lattice energy is higher than the magnitude of its hydration energy. Magnitude of lattice energy is greater than magnitude of its hydration energy. That's why the enthalpy of solution is endothermic. There is some other version of a question that maybe we would do before. There is some other version of a question that we need to know. What if you're given different enthalpies What if you're given enthalpies? If they say the standard heats of formation, they gave the standard heats of formation. Of ethanol, carbon dioxide, and water are negative 277, negative 227.0, negative 393.5, and negative 285.5 kilojoules per mole, respectively. Draw a Haber cycle grab on Haber cycle to relate energy changes. Two, calculate the standard enthalpy, calculate the standard heat of combustion. Calculate the standard heat of combustion, of combustion of ethanol using the Born-Haber cycle above. Let's see. Now here we've been given enthalpy of formation of ethanol. So enthalpy of formation, this is where 1 mole of a compound is formed from its constituent elements. Since ethanol is CH3, CH2, OH, you can see that we need carbons, we need hydrogens, and oxygens. So we shall say that carbon, solid, plus hydrogen, gas, plus oxygen, gas, we shall be forming ethanol, CH3, CH2, OH, and this is in liquid state. So this is the enthalpy of formation of ethanol and this will be negative 227 as given. Then now they said enthalpy of formation, the standard enthalpy of formation of ethanol, carbon dioxide, and water. So basically here, we shall find out that for carbon to form carbon dioxide and for hydrogen to form water, this is liquid. Here we need 2 oxygens to form this. So we shall have 2 oxygen gas, and here to form water, we shall need 3. We shall need 3 out of 2 oxygen molecules. If you put the equation, that is what we shall need. So basically, the form here we shall have 3, here we shall have 2, and this one has to give us ethanol. Sorry. Ethanol undergoes combustion because they want standard heat of combustion. So when ethanol undergoes combustion in 3, you first write the equations aside. Actually, that is the easiest trick. First write the equations aside and then get the products. Yeah. So ethanol undergoes combustion to give us carbon dioxide and water, but it needs 3 oxygens. Carbon, for it to form oxygen, it has combined with 2 moles of oxygen. Hydrogen to form water, it needs combined with 3 out of 2 moles of oxygen. So you realize that This is enthalpy of combustion that they're interested in. And here we shall have 3 on this part. We shall have 3 times the formation of water as given as 285, yeah, negative 285.5. Then, because that is what we are forming 3 molecules of water, what here we are forming 2 molecules of carbon dioxide. So it will be twice enthalpy of formation of carbon dioxide, which will be twice enthalpy of formation of carbon dioxide, negative 227, yeah? Sorry, negative 393, negative 393.5. Why? Because we are forming 2 molecules of carbon dioxide, we're forming 2 molecules of water. Here we form 1 more, and this is undergoing combustion. So if they want us to calculate the enthalpy of combustion, we just need to apply Hess's law. By Hess's law, we are going to find out that twice enthalpy of formation of carbon dioxide plus 3 times enthalpy, because we are forming 3 moles, so that's why we multiply by 3. Formation of water, yeah, is going to be equal to the enthalpy of formation of ethanol plus the enthalpy of combustion of ethanol. So we need enthalpy of combustion. So you can substitute. This will be twice carbon dioxide is negative 393.5, then plus 3 times the one of water, negative 285.5, is equal to combustion of ethanol, that is negative 277, and plus enthalpy of combustion. So calculate for enthalpy of combustion, and it is going to give you negative 1416.5 kilojoules per mole. So here is always a question that basing on your calculation, you give the appropriate use of ethanol. The appropriate use of ethanol, is simply being used as fuel because its enthalpy is highly exothermic. You can see that we have the highest value of enthalpy of combustion. So it is used as fuel since it gives out a lot of heat. I wish you well. In our next video, we shall see how bond Haber cycles can be used to calculate the bond energies under some reactions.